So in the previous sessions we are discussing about various categories of operators in the C language. So among various categories we have already seen the arithmetic operators, and then relational operators and increment and decrement operators. In this session let us have a look on bitwise operators. Bitwise operators. So the bitwise operators are bitwise and bitwise or, bitwise XOR, bitwise NOT or complement, right shift operator, left shift operator. So all these are various bitwise operators. So bitwise AND, bitwise OR, bitwise XOR, bitwise NOT or a complement, right shift and left shift. So one main thing is here these bitwise operators can be performed in between the integer values, and the result will be also an integer value. The result will be an integer value. For example, if A is having some 5 and B is having some 4, so we can use this bitwise AND as A and B. A and B. So 5 and B. It will also gives the result as integer value. So before 5 and 4 will gives integer value. So before going to this, we have to learn the conversion of decimal to binary. So decimal means our integer values, and this AND operation or XOR, NOT, right shift and left shift operators will be performed in between the binary values. So the procedure is, first the decimal value will be converted into binary, and then the operator will be performed, and again the resultant will be converted into decimal. So for this purpose we need to know the procedure of converting decimal to binary and a binary to decimal. So let us have a brief look on that, and then we will go on with the individual operators. Decimal to binary. Decimal to binary conversion. If let us take some value here as 5. The value is 5, and now we need to convert this 5 into binary. So this is decimal. We need to convert into binary. So as we know that binary language means that is only the combination of zeros and ones. So except zeros and ones, no other number will be in this binary language. So we have to convert this decimal into a binary. Let us see the procedure. So binary means only 2 bits, right? 0 or 1. Now divided by 5 with 2. So 2 2s are 4. What is the remainder? 1. Again 2. 2 1s are 2. Remainder 0. Right? So it is not divisible. So leave it and write this order from low to high, or simply we can say that bottom to top. Bottom to So 5 can be represented as bottom to top 1 0 1. So we have to divide with 2, so that we have to write the quotient and remainder. Again we have to divide it by 2, write the quotient and remainder. So automatically arrange the bits from bottom to top, so that we can get the binary equivalent of decimal number. So let us take one more example so that you can clearly understand. So let us take some 11. So binary equivalent, we have to find out the binary. So apply the procedure, divided by 2, 2 5s are 10, so the resultant, the remainder is 1, and again it divided by 2, 2 2s are 4, again the resultant, the remainder will be 1, again 2 1s are 2, 0. Now arrange the bits from bottom to top. So 11 can be written as 1 0 1 1. So this is the binary equivalent of the decimal number. So this is the procedure to convert the binary format of any decimal value. Any decimal value, you can take any decimal value. This is the procedure to find the binary equivalent. Now what is the reverse procedure? That means binary to decimal. So how the binary equivalent will be converted into decimal? So that is also a simple step. Here this is 2, that means the return will be 1011 base 2. So if it is base 2, it is automatically, that means it is a decimal value. So write down 1 0 1 1. Let us take this one, this example 11. Now we are converting this 1011, which is a binary equivalent of 11, into the decimal value, that means 11. How to get the 11 value 11? So from rightmost, this is 2 power 0, 2 power 1, 2 power 2, 2 power 3. So if there are 5 bits, 2 power 4, 6 bits, 2 power 5, 7 bits, 2 power 6. So likewise we have to write from right corner to left side, right to left. So now multiply this one. So see, 1 into 2 power 0 plus 1 into 2 power 1 plus 0 into 2 power 2 plus 1 into 2 power 3. Hope you understood the bit and this one, multiply this one, plus second bit and second power, plus third bit and 2 square, plus fourth bit and 2 power 3. Now calculate this one. 1 into 1 1 plus 1 into 2 2 plus 0 into 4 0 plus 1 into 2 cube 8. So this is 8 plus 2 10 plus 1 11. So this is the simple procedure to convert any binary to decimal value. So here if we use these operators, bitwise operators, AND, OR, XOR and complement or not, right shift and left shift, we have to first convert the decimal value into binary, and then the binary will again convert into decimal for the resultant, right? So hope you understood the procedure, how to convert the decimal equivalent to binary and the binary equivalent to the decimal number. Now let us take each operator and let us have a look. See here, the bitwise AND is represented as ampersand, AND symbol. Bitwise OR, it has 2 lines, So you can find this notation in the keyboard. There is OR, bitwise OR. So don't get confused, because there is a similarity between bitwise operators and the logical operators. If you write this double AND, it will be logical operator. If you write this double OR, it is a logical OR. So don't get confused. So a single one. So AND, bitwise AND, OR, bitwise OR, and cap symbol. Cap symbol, it is a bitwise XOR, and tilde symbol, it is a bitwise NOT or complement, and two less than symbols, that is right shift. Sorry, two greater than symbols, that is right shift, and two less than symbols, that is left shift. Now let us have a look on each operator. First, coming to this bitwise AND. Bitwise AND. So it is represented as AND. It is represented as AND. So let us have a look. If A is equal to 4, B is equal to 3. A is equal to 4 and B is equal to 3. Then we have to perform A and B. We have to perform A and B. So for this purpose, first we need to convert into this binary, and we have to convert B into binary, and the resultant will be applied, AND operation, and again we will get the result as binary. Again we need to convert it into decimal. So this is the procedure we need to apply. So first step is we have to convert the A value into binary. So 4 is converted into binary. 2s are 1, 0. The resultant is 0, 2, 1, 0. So from bottom to top, we can have the 4 as 1 double 0. 4 double 0. Sorry, 1 double 0. Similarly 3. Again convert into 3. 1s are 2, 1. So obviously from bottom to top, that is 3 can be converted as 1, 1. So here 3 bits, here 2 bits, we can include a 0 on left side. Left side we can add 0, so that the value will not change. So generally any binary, any decimal value can be represented in 4 bit or 8 bit. So generally a 4 bit representation will be as 8421. So a normal numbers. So that is 0 to 15 numbers. 0 to 15 numbers can be represented using 4 bits. 0 to 15 can be represented using 4 bits. That is 8421. That is 2 power 0, 2 power 1, 2 power 2, 2 power 3. So here, so 4 can be represented as a 4 bits, that is 0, 1, double 0, and 3 can be represented as 3. 3 means this bit and this bit must be addition. 0, 0, double 1. So same 1 double 0, 0, triple 1. So we can represent in 4 bits or 8 bits, anything else. So here for AND operation we can represent in 4 bits. That's no problem. And AND operation, for AND operation, if so here 1 is represented as true and 0 is represented as false. So 2 bits, let us write all the combinations. So 0, 0, 0, 1, 1, 0, 1, 1. So 0 and 0. So if both are zeros, obviously the resultant will be 0. If one is true and one is false, the resultant will be false. Here also same, one is true and one is false, the resultant will be false. If both are true, then only the resultant will be true. That is the AND operation. So only if both are ones, then we can get the resultant 1. Except this one, all the remaining cases will be zeros. That means any one is false, the resultant will be false. So let us apply for this one 4 and 3. For this 4 is represented as 0 1 0 0. 3 is represented as 0 0 1 1. Now perform the AND operation. 0 and 1. Here 1 is false, 1 is true. The resultant is 0 1. So this is the resultant. So 0 1. The resultant will be 0. Again 0 1. Again 0. 1 0. 1 0. 0. 0 0. 0. So the AND operation for 4 and 3 will be 0 0 0 0. So let us convert into decimal. So this is in a binary format. We have to convert it into decimal. See, first we have performed the binary of A, next binary of B. Then we have applied AND operation. We have applied AND operation in between binary equivalents. So we get the binary resultant. So this is the binary resultant. And the last step is we need to convert it into decimal equivalent. So the decimal equivalent of all zeros is obviously 0. So 2 power 0, 2 power 1, 2 power 2, 2 power 3. 0 into 2 power 0, 0, 0 into 2 power 1, 0, 0 into 2 power 2, 0, 0 into 2 power 3, 0. So after adding all these things, we will get simple 0. So that means here the A and B is equal to 0. The result will be 0. Right? So the procedure, we need to convert into binary and then we have to apply the AND operation. That means if any one is false, automatically the resultant will be false. If both are true, then only we can get the true as a resultant. So applying this for the both binary equivalents, so we will get the binary resultant. So we need to convert it into decimal, that is 0. That will be the answer for A and B. That is a bitwise AND operation. Now let us look on bitwise OR, one more operator. So let us take the same example. Let us take the same example, bitwise OR. The representation is 2 lines. So A or B will be, what is the result? So A, for 4 binary equivalents this one, 3 binary equivalent this one. Let us apply OR. So here OR operation, write the combinations 0 0, 0 1, 1 0, 1 1. So here the quite opposite to the AND operation. That means if any one is true, the resultant will be true. So here both are false, so the resultant will be false. Here one is false, another one is true, the resultant will be true. Here one is true, another one is false, the resultant will be true. Here both are true, automatically it's true. So here OR operation, if any one is true, the resultant will be true. So let us apply for this 4 or 3. Let us write the binary equivalent 0 1 0 0, 0 0 1 1. Apply the OR operation. So 0 and 1. So one is false, another one is true. Here one is false, another one is true, the resultant will be true. That means 1. Again 0 1, 1, 1 0, again 1, 0 0. So here both are false. So the resultant will be 0. This is the binary equivalent for 4 or 3. Now convert it into decimal. Now convert this binary equivalent to decimal. So 2 power 0, 2 power 1, 2 power 2, 2 power 3. So 1 into 2 power 0, that means 1 plus 1 into 2 power 1, 2 plus 1 into 2 power 4, 4 plus 0, 0 into 2 power cube. That means 4 plus 2, 6 plus 1, 7. So the resultant of 4 or 3 is 7. A or B will be 7. Hope you understood this OR operation. Here, if any one is true, the resultant will be true. Let us have a look on one more operator, that is XOR operator. Again we will continue with the same example, same values. bitwise XOR, that is cap. Here A or B. Here in this XOR operation, let us write the combinations 0 0 0 1 1 0 1 1. So only 4 combinations will be there for the 2 bits. Here there is a rule, that is one must be true and another must be false, then only the resultant will be true. So once again I will repeat. So one must be true and one must be false, then only the resultant will be true. If both are true, automatically the resultant will be false, and if both are false, that also the resultant will be false. Here both are false, the resultant will be false. Here one is false, another one is true. So 2 variations, that means 1. Again one is true, another one is false, again 1. Both are true. Even though both are true, the resultant will be 0 for XOR operation. So the only rule is one must be true and another one must be false. So 2 combinations must be there. So for that resultant only we will get the result as true, that means 1. Now let us apply A cap B, that is 3 cap 4, means 0 1 0 0 0 0 1 1. Here 0 1, so 1 is true, another one is false, resultant 1. 1 is false, another one is true, resultant 1. 1 is true, another one is false, the resultant 1. Both are false, the resultant will be 0. The same result we got. That means the decimal equivalent is 7, which we get for OR operation. So A XOR B will also give the result as 7. So first we have to apply the binary, we have to find the binary equivalent of given decimal, and then we have to apply the operator based upon these tables, and then we will get the binary equivalent, and next we need to convert the binary equivalent to decimal value. So hope you understood this XOR operation also. And let us have a look on next operator, that is complement or not. Bitwise not. So this not operation can be performed on only one variable. So either we can say it as not A or not B. So A not B is not valid statement, valid expression. So this not symbol can be performed on a single operand, that means variable, single variable or a single value. So here that is simple. If it is having one complement, that is 0. If it is having 0, it will be 1. The resultant will be 1. For the not operator, if the value is true, the resultant will be false. If the value is false, the resultant will be true. So that is the rule for this not operator. Let us have a look. Not A. So for this, the binary equivalent is 0 1 0 0. So for this not operator, so here 0, so it will be true. Here also 0, it will be true. Here 1, that means false. Here 0, that is 1. So this is the binary equivalent, that is a complement. We can say it is a complement or one's complement. So the binary value for this one is 2 power 0, 2 power 1, 2 power 2, 2 power 3. So 1 into 2 power 0, 1, plus 1 into 2 power 1, 2, plus 0 into 2 power 2 square, that means 0, plus 1 into 2 power cube, 2 cube, that means 8. So the resultant will be 8 plus 2 plus 1, that means 11. So not A is 11. This is a bitwise not. Here the compiler may gives the result as negative result. So that means it will give the result as a 2's complement. After performing this not operator, bitwise not, the resultant will be the 2's complement. So the 2's complement means 2's complement. So negation n is nothing but minus n plus 1. Simple form. Negation of n. N is in a binary equivalent, right? So negation n is minus of n plus 1, where n is a binary equivalent. So we need to add 1 for binary equivalent, that we call it as 2's complement. So after performing this not operator on a variable, the result will be in 2's complement. So this is a 1's complement. This is also right, but the compiler gives the result in 2's complement form. That means not n will be minus of n plus 1. So let us have a look for that. Here n is 4. N is 4, that is 0, 1, 0, 0. N is 4, that is binary equivalent 0, 1, 0, 0. So not n is minus n plus 1. So we need to add 1 for this binary equivalent. So add 1. So 0, 1, 0, 1. So this is the resultant after adding 1 to n. So this one is the 0, 1, 0, 1. Now convert into decimal. 2 power 0, 2 power 1, 2 power 2, 2 power 3. So 1 plus 0 plus 4 plus 0. That means 5. So the result will be 5. Here the negative symbol, so negative 5, minus 5. So if you use the not a, if a is 4, the resultant will be minus 5. So it will be minus 5. This is in a 2's complement. This is in a 2's complement. So both are right. So not a not operator bitwise not means if it is false, we have to write it as true. If it is true, we have to write it as false. Here we have converted it into not operator. We have operated the not operator and we get the result as 11. And applying this 2's complement, that means minus n plus 1. That means we have to add 1 for this 4. So we got this minus 5. This is in a 2's complement. Hope you understood this not operator. So somewhat complex, but very simple. And let us look about this shift operators. Left shift operator. So we have to mention how many bits we have to left shift. Here a left shift 2. That means we need to shift the value of a with 2 bits. So this will be general. In general, this will be done on 8-bit conversion. 8-bit representation. So 8-bit representation for this 4, the 8-bit representation is 0, 0, 0, 0 and 0, 1, 0, 0. 8-bit representation for 4. So all the remaining will be for zeros. So 2 bits we have to shift on left side. That means this will be shifted towards left side. So every bit should move towards left from this one. So 0, 0, 0, 1, 0, 0. So see this one. So only 6 bits. What about the remaining 2 bits? Add zeros. So this is the left shift. Now convert it into decimal. That means 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, 2 power 7. So this one 0 plus 0 plus 0 plus 0 plus 2 power 4, 16 plus 0, 0 plus 0. So if you add all these things, we will get 2 power 4, that is 16. So the result of A shift 2 is 16. So first here we have to represent in 8 bit. So 4 is represented as 8 bit, 4 zeros and 0 1 double 0. Now we have to shift on 2 bits, left shift. So 2 bits will be shifted and move every bit towards the left side. So we will get the result as 16. Similarly, the right shift. Right shift. Here also the procedure will be followed with 8-bit representation. So A, right shift 2, towards right. So towards right with 2 bits. Now binary conversion. So 8-bit representation of 4, 0 0 0 0 0 1 double 0. Right side. So move this way. These 2 bits towards this way. So move all the remaining bits towards the right side. Now see 1 0 0 0 0 0. Again there are only 6. Add zeros on left side. So this is the result for right shift. Now convert it to decimal. 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6 and 2 power 7. The resultant will be 1 0 0 0 0 0 again 0 0. Add all these things, you will get the result as 1. So if you apply the right shift with 2 bits on A, the result will be 1. A simple operations. So hope you understood these right shift operator. So these are all the various bitwise operators. Bitwise AND, bitwise OR, bitwise XOR, bitwise NOT, right shift and left shift. So all these bitwise operators will be performed on binary equivalents of decimal values, and the resultant will be also a binary, but we will get the conversion from binary to decimal and the resultant will be in decimal format. So for that purpose, first we need to take a value in a decimal form, and first we need to convert into binary format, and then we have to apply the operation. So we will get the binary equivalent, and again that binary equivalent will be converted into decimal format. So this procedure will be done by the compiler itself. So we need to cross check after getting the result. So if we give A right shift 2, the result will be 1. So all this procedure will be done by the compiler itself, the conversion of binary and again the conversion of binary to decimal. So we will only get the result in decimal value. But the procedure, how we get the decimal value, the procedure is this one, completely in binary format. So hope you understood this bitwise operators. So let us stop here, and in the next session we will discuss with 2 more categories of operators. and thank you.